Alright, in this video, the last video, is about the runs test. The runs test is a very simple test to determine if a sample is random or not. Let me write the definition down. A run is a sequence of data having some particular characteristic. Whatever that characteristic may be, whatever characteristic of interest, I guess, is what we should be talking about. Each run is preceded by and followed by data with a different characteristic. The number of data in a run is called the length of the run. As an example, a coin is flipped 10 times. Let me do a few examples here. Suppose we get H, 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 followed by all T's. So there's our 10 flips. We have 2 runs. I'm looking at this guy right here. That'll be our first run. And then this second one right here will be our second run. So the H, 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 H is a run of length 4. T, 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 T is a run of length 6. Now instead of what we got there, let's suppose we flip and we get the following. Suppose I get H, T, T, H, T, T, H, T, T, H. Let me make sure that's a total of 9, that is. And so we have a bunch of runs here. Here's a run right there. So that's our first run. There's our second run. That's our third run. There's our fourth run. Fifth. Sixth. And finally, seventh. Total of 7 runs, and they vary in length from 1 or 2. Another definition. The runs test for randomness is a non-parametric test that can be used to determine if a sequence of sample data is random when a sequence has too few or too many runs. Chances are that sample is not random. So for example, if I flipped my coin 10 times, 10 flips, this would draw our suspicion. There's only one run there, and the run is of length 10. That looks very suspicious, and we would suspect that's not random. Or even something like this. Suppose you do get something that is exactly what you're supposed to get according to probability. It should alternate between heads and tails and heads and tails. But nonetheless, this here is suspicious because now you have 10 runs. There's too many runs in this case. So some mixture, something in between these two is what we're talking about as far as being a random sample. These two are too suspicious. All of our hypotheses take the form H naught, the sequence of data is random, or H sub A, the sequence of data is not random. And this is a two-tailed test. For a sample, let n sub 1 equal the number of data with one characteristic, and then n sub 2 is the number of data with another characteristic. And then the capital letter G will stand for the number of runs. We'll use the runs table to determine critical values. The test statistic is complicated only because we have two different cases. We have for n sub 1 and n sub 2 less than or equal to 20, the test statistic is G, which equals the number of runs. For n1 greater than 20, or n2 greater than 20, the test statistic is z equals g minus mu sub g over sigma sub g. So you can see it's a standardized normal calculation. Our mu sub g equals 2n1 n2 all over n1 plus n2, and our sigma sub g equals the square root of 2n1 n2 times 2n1 n2 minus n1 minus n2. All of that inside of the square root is divided by n1 plus n sub 2 squared times n1 plus n2 minus 1. There's really no difficulty in this computation. It's just lengthy looking. Performing a runs test for randomness. State h sub 0, h sub a, specify alpha, determine n sub 1, n sub 2, and g, determine critical values, so you have the two cases, n1 and n2. If they're both less than or equal to 20, use the runs table. And B, if either n1 is greater than 20 or n sub 2 is greater than 20, use the normal table. Remember, it's always two-sided. Compute the test statistic so when n sub 1 and n sub 2 are less than or equal to 20, the test stat is G. But if either one of them is greater than 20, the test stat is Z equals G minus mu sub G over sigma sub G. And then, as usual, after all this is done, make the decision. All right, here's the first of two examples that I'm going to do. I want to take a look at various runs. So let's take a look at this first one. Here's a run of 1. Then I have a run of 3. Then I have 1, 2, 3, 4, 5, 6, 7. Try to keep track of these as I go. So that's 7, 3, 1. 1, 2, 3, 4, 5, 6, 7. Here's another 7 that's all D's. And then I have an R, another 1. In between here is going to be tricky. Then I have a 2. And then I have a 1. Look at the size of that one. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. and then here's another 1. And the well, actually, I did that wrong. These 2 and this 1 belong together. So let me take that 1 out of there, and I'm going to call that a 3. And then I have some D's here. That's a 4. Some R's, that's a 3. There's a 1. There's a 2. There's a 4. And there's a 2. So let me get my numbers down here. Let's start with n sub 1. I'm going to let that be the number of R's. And then n sub 2 will be the number of D's. So let's take a look then. For the Republicans, how many do I have? I have 1 plus 7, that's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then the number of the number of Democrats, we have 3 plus 7, there's 10, plus 2 more is 12, plus 13 more is 25, plus 4 more is 29, then 30, 34. So we have the case where n sub 2 is greater than 20. So we're going to use the z table ultimately. G is the number of runs. And how many does that equal? Well, that R is the first one. Then we got 3 D's. That's the second one. Then the third one, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th. So I get a G of 15. Now let me state my H sub 0 and H sub A. The sequence of data is random, or the sequence of data is not random. Now, unless it's stated otherwise, let me take a look at the problem at hand. The problem at hand does not state any alpha. What we are doing in this section, because there's multiple tables and things like that for various alpha, we are going to always assume in this particular section that alpha equals 0.05. And inevitably, you're going to have to cut that in half because, like I said, it's a two-sided test. So you're going to have to work with that. Then if I want to get my z sub 0, my critical value, you can use your calculator and use the inverse norm function on it. So remember, if you can find that second above bars, you'll see we have inverse norm. So let me go ahead and grab number 3. And I'm going to want to put 0.025 and enter my way through this. Now it's going to give me the left value, which is negative 1.96. So you know the positive value, the other tail, is positive 1.96. So we have plus and minus 1.96. A picture would look something like this. And so there's my critical regions defined. Let's go ahead and calculate our statistic, or test stat. That's z equals g minus mu sub g over sigma sub g. Mu sub g equals 2n1 n2 all over n1 plus n2. The n1, let's see what we had, was 20, and the n2 was 34. So 2 times 20 times 34 divided by 20 plus 34. And I'll just do it on my calculator. I'm going to do 2 times 20 times 34, and the denominator is equal to 54, so I'll just put 54 instead of worrying about parentheses. And I end up with about 25.185. All right, then sigma sub g, that one is much more complicated. 2n1 n2 times 2n1 n2 minus n1 minus n2. All of that stuff is divided by n1 plus n2 squared times n1 plus n2 minus 1. And so let me plug my numbers into there. 2 times 20 times 34. In parentheses, I have 2 times 20 times 34 again, minus 20 minus 34, all over 20 plus 34 squared times 20 plus 34 minus 1. Now, you can do this in a number of ways on the calculator. I'm just going to try to do it in one shot and see what happens. You can probably cut it into pieces if you think this is too much to do in one shot. But let me go ahead and start my square root. And then I'm going to have my 2 times 20 times 34. Let me start my parenthesis. 2 times 20 times 34 minus 20 minus 34, end of the parenthesis. Notice I'm still under the square root. You can see that square root over bar is covering up, is on top of my cursor. Now let me hit my division. Now you're going to want to encase the entire denominator in parentheses. That means the bottom parentheses will start with 2 of them. I'll put my 20 plus 34. Let me end that, square it, times 20 plus 34 minus 1. And then I need to put a parenthesis around that to ensure that the whole thing is enclosed inside of the denominator. And I end up with about 3.390. So when I do this, I'm going to have 15 minus 25.185 divided by 3.390. Now let's see what our calculator comes up with for that. I'll move it out of my way. At least I thought I did. This time I'm going to encase the numerator in parentheses. 15 minus 25.185 divided by 3.39. Enter. So I have about -3, well, approximately -3. Now let me come back up to my critical regions, and we see that this -3 is inside of the critical region, so we reject H0. So this sample does not seem like it is random. All right, here's another example. This time we are looking at a number generator that outputs digits, and we're concerned with whether they are even or odd digits. So let me count the runs and the number of items in the runs. Starting with the O's, that has 3 items. Then the E's has 4 items. These O's, how many are in there? There's 5 of them in there. 4 E's, there's another one. 2 O's. So I'm marking down the length of each of these runs. So I think I've got all of them. Let's let N1 be the number of O's. Let me make that make O's. And then N sub 2 will be the number of E's. So let's take a look at the number of O's first. I have 3 plus 5 plus 2, so I'm at 10, 14, 16. Looks like I have 16 O's. And then N sub 2, the E's, I have 4 sets of 4, so I have 16 E's. So now we have a situation where N1 and N2 are both less than 20. So now we look at the letter G to determine what we do next. So if I look at the letter G, that's the number of runs. So let me count them up. I have 1, that's for the O's. Then I have 2, 3, 4, 5, 6, 7, 8, 9. So G is 9. And let's take a look at our critical value. You know what? I completely forgot to put my H naught and HA. The sequence is random, or the sequence is not random. And remember, we were always assuming that alpha equals 0.05. Now, we won't do anything with alpha for this table, but let's go ahead. Do I know what I want to call this critical value? Let's call it G sub 0. And let's pull up the table. All right, here's the runs table. You see that you have N1 along this side, the left side, and then you have N2 along the top. Remember, it doesn't matter which one you call N1 and N2. This table is symmetric either way. So for our case, we have an alpha, well, actually, I don't need to know alpha at all for this table. I don't see any alpha. I do need to know N1 and N2, and both of those were 16. So for N1, if I go down to 16, and then go over to N2, which is also 16, I see I have a numbers 11 and 23. So let me go ahead and put those in. This is weird to look at it, but you see that this is 11 or 23. What that means is if the test value falls between 11 and 23, we do not reject. But if it's less than 11 or greater than 23, we reject. So basically you want to look at it this way, I think. Let me put my 11 here, my 23. Anything out here or out here is rejection. And then inside of here, in between the 11 and 23, is do not reject. What they're basically telling you here is that if you go over 23 runs, that's too many. If you have less than 11 runs, then you have too few. Anywhere in between is just right. That's how they determine randomness, is to determine if it's just right or if there's too few or too many. In our case, the 9 is less than 11. Since 9 is less than 11, we have that G is less than G naught, which implies that we reject the null hypothesis. Make a note, though, for yourself that had my G come out to be greater than 23, I also would have rejected in that case as well.